Greetings and welcome to another installment of QuantSlob. This is 17 in our basic application series. This time around, we're going to take a peek at part 2 of the basics of counting, or combinatorics. Recap. Counting combinatorics is all about selecting values or objects. So, for example, how many different 3-topping pizzas can be made from 6 available toppings? In the language of combinatorics, 6, choose 3. Well, one of the ways we can get to our answer is to simply enumerate or count all of the possibilities. And doing so, we find that there are 20 possible 3-topping pizzas that can be made from 6 available toppings. 6 choose 3 is 20. We can find the answer to how many 3-topping pizzas can be made from 6 available toppings in Pascal's triangle. In fact, we can find the answer to any n choose k problem. No problem. Here in this example, we visit row 6 here, starting at choose 0, which corresponds to the far left 1 here. We count over to the 4th entry, choose 3, and we arrive at our answer, 20. Notice that here in Pascal's triangle, the row sums, that is the sum of the numbers in each row here, is equal to the number 2 raised to the power of the row index. For example, the row sum of row 6 is equal to 2 raised to the 6th power, which is 64. So returning to pizzas, thinking about pizzas, what this means is that if we have 6 available toppings, there are a total of 64 different pizzas we can make. For example, there is only one way we can make a pizza with no toppings, and there are 6 ways we can make a 1-topping pizza, one for each available topping, and so on. There's a more direct way to compute n choose k. And here's the equation, and there's a lot going on here, so let's break it down. Let's take a look. On the left-hand side of the equality here, we have a capital C here that is subscripted with k and back subscripted with n here. This is the common mathematical symbol that means, or reads, n choose k. The exclamation mark here that we see appearing 3 times on the right-hand side of the equality denotes the factorial operator. And of course, factorial is named after the great mathematician and frame welder Cooter Factorial. Am I not logging out of my computer at night? I keep doing that. I sincerely apologize. The factorial is not named after anyone. I'm quite certain of that. A little piece of advice for all of you. Screen your interns. Anyway, the factorial is sort of a cumulative product performed on the collection of all counting numbers up to and including the integer value that precedes the exclamation mark. So that's a big mouthful, but it's really easily conveyed by example here. So 5 factorial, for example, equals 5 times 4 times 3 times 2 times 1, which equals 120. Notice here, for the sake of simplicity, that 6 factorial is equal to 6 times 5 factorial. So all's well and good. But one wrinkle we need to know about is the somewhat counterintuitive fact that 0 factorial is defined as 1. Now, I say counterintuitive, but if we look at this through a mathematical lens, it makes perfect sense. The unit, the number 1, is the identity in multiplication, and 0 factorial really represents an empty product. So it makes sense. Anyway, let's go ahead and take our combination equation for a spin here. So back to our 3-topping pizza. 6 choose 3. We can solve this no problem here with our formula. So let's go ahead and expand this out. We notice that here we have a lot of cancellation after we've expanded out the numerator and the denominator. And needless to say, computers nowadays can solve these sorts of combinatoric problems effortlessly. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.